1 second. Arun, can you hear me?
Yeah, I can.
Okay, great. Yeah.
So, very good afternoon, everyone. So, welcome to today's seminar. Today, we have Professor Manoj Puravankara from TIFR as our speaker. And I would like to invite Dr. Brijesh Kumar to introduce the speaker. Dr. Brijesh Kumar.
Yeah, good afternoon, everyone. I welcome you all. To this session, and with us we are having today Dr. Manoj Puravankara, who is a faculty at TIFR in the Department of Astronomy and Astrophysics, and actually he completed his PhD in 2005 from IA Bangalore. Then after doing a couple of postdocs, he joined back the TIFR. And his interest lies in the star formation studies and also the instrumentation for infrared group. And he's visiting us here as a part of our DTAC member, and there's a time allocation committee meeting tomorrow and day after. So he's with us for any discussion and all that. And he's one of the special aim, visiting us is also because he's proposing one instrument, multi-object spectrograph for DOT. And this instrument is a precursor to the NLOT instrument and also connected with TMT. Probably he'll speak more about it. So he is free to discuss with the Aries team, jointly, since it is coming on DOT. So he's open for discussion, and students and postdoc, they can also discuss and ask questions in that regard. And also recently, this infrared group at TIFR is very, very active, and they have been conferred the ASI 2023 Jubin Kembhavi Award for a very significant contribution in instrumentation and observational science in infrared group. So congratulations to Dr. Manoj, because you're part of that infrared astronomic group. And we welcome you again. Just start to talk.
Thank you, Brijesh, for those kind words. Yeah, it's true that the infrared group at TIFR won the Subin Kembavi Award. Although Brijesh congratulated me, I think the credit really deserved to our leader, Professor D.K. Oja. So I'll convey your congratulations to him. Yeah, it's nice to be here, and I wanted to come here earlier, and I'm not here just for the DTAC meeting. I also wanted to come here and talk to you about this instrument which we are developing at TIFR, which is a multi-object spectrograph and a wide field imager, 9 arc minute by 9 arc minute imager working in the near infrared wavelength, 0.9 to 2.5 microns. See, this combination of wide field imaging and multi-object spectroscopy is a powerful tool to address many of the astrophysical problems that people are investigating currently. So this is the instrument that we are building, and I am the PI, and Professor Bashruti Mukherjee of TIFR is a co-PI. Arun Surya, who is now a faculty at IIA, who has been a postdoc with our group for the last 3 years. He moved to IIA last November. So he has been instrumental leading the optical design and various other aspects of this development. And rest of the IA group, all our IA group engineers. There is a bit of a history to this. Oh, I think I had to click once here. Yeah. So just to provide you a context and a little bit of background to this whole thing. So as I said, in the next 2 decades, many of the foundational or important questions in astronomy, astrophysics require multiplexing and studies of ensemble of objects, not just stars and stars, planets, galaxies. So multiplexing is a necessity. So you can't, and also when you go from 2-meter, 3-meter class telescope to larger aperture telescopes, 8 to 10-meter class telescope. Single slit spectroscopy is no more time and resource efficient. So you need to go to multi-object spectroscopy. So that was our motivation. And then this whole idea started when the TMT project was going on. I mean, it's still going on, of course. But TMT had 3 first light instruments earlier. And one of them was called IRMS, a multi-object spectrograph. And it was supposed to be a clone of the MOIS instrument on the Keck telescope, 10-meter Keck telescope, where it had this configurable slits. So we wanted to, TIFR wanted to be, IR group wanted to take up a work package of TMT of this IRMS instrument. So we thought we'll have our own development parallelly. So then, we thought for a large aperture NLOT kind of telescope, we could use this technology. So we started that way. And then we started a proof of concept and design of a study of a multi-object spectrograph and a configurable slit unit. But then the TMT, what happened was this IRMS is no more a first light instrument on TMT. That is replaced now by MOIS. See, in the last 6-7 years, what has happened is exoplanet field has kind of taken over. So there's an instrument called MOIS, which gives you, again in the infrared, maybe it goes slightly into the mid-infrared, which gives direct spectra of exoplanets. So IRMS will come as a second generation instrument for TMT. But still, such a multi-object infrared spectrograph is a must for NLOT. So we continued this. Then we realized during the proof of concept study that particularly this configurable slit unit, which is the most attractive feature of our spectrograph, that we could actually develop a prototype and deploy it on DOT. So initially, see, for example, the MOIS on Keck has 44 slits. But the prototype that we are thinking of for DOT will have only 5 slits. See, it scales with the telescope aperture. So we just wanted to demonstrate this. So we thought that will be a good idea. And we started this development a couple of years ago. TIFR gave us 2 crores of seed money. And that we have done quite a bit on this. And another motivation was the Indian NLOT efforts are gathering momentum now. In the last 2-3 months, there have been bi-weekly meetings, etc. So this is the right time to build multi-object spectrographs as a multi-institutional consortium. So IAA, Arun is at IAA, and I'm here to sort of talk to you about this instrument and then kind of welcome you, invite you to participate in this endeavor. So what is multi-object spectroscopy? So single slit spectroscopy, you just put one object here and then you get spectra. But multi-object spectroscopy is, you get multiple slits and, you try to get multiple spectra on that. So traditionally, multi-object spectrograph were realized using what are known as the laser cut mass. So for example, Subaru's first light instrument, MOIS, was like that. What you do is 2 days before your observation, you image your field and you know where exactly the stars are. And then you, on a metal sheet or something, which will be cool, you cut the slits and then put it in front of the instrument. One disadvantage for this is you have to have 2 DEVAs. You have to cool that separately, right? It is kind of a detachable thing. So, the laser cut mass has several disadvantages. So instead, this configurable slit units, what we do is, so this is your field of view, okay? Let's say this is your 9 arc minute by 9 arc minute field of view. Then there is bars come from both sides and form a slit. So you can have as many numbers. So for example, MOIS on Keck has 44 slitlets. So you have 88 bars, coming from both sides. And then you get spectra like this, right? So for each, I'll show you in the next slide, it will become clear. See, now they have formed the slits. The bars have come from both sides, so there will be a small gap here, which I have shown in red. So, and this is the dispersion axis. So you get multiple spectra. So this is the idea. The advantage is you can change the slit width and the slit position in real time. So it offers you tremendous flexibility. And configurable slit units, spectrographs, have some heritage. I told you Keck MOIS, which has 46 slitlets and a field of view of 6.1 by 3 arc minute. YGHK pipe. And GTC, the Spanish 10-meter telescope, the EMIR spectrograph, that 55 slitlets, in YGHK. So the long-term idea is to build an instrument like this for NLOT. And how do you build an instrument for a 10-meter telescope when you have no experience building it? You try to build a prototype for a smaller one and learn in that process. So that is what we are doing here. So let me give you an overview of what we are proposing. Multi-object infrared spectrograph. We are designing it for DOT. So we are working with 5 configurable slits. And of course, this is a pathway instrument for NLOT. And we have made a lot of progress in the last 2-3 years. Optical design is finalized. The configurable slit we have actually tested in the lab. I'll show you some of the interesting results. And we have successfully demonstrated the movement at cryogenic temperatures. We have gone down to up to 140 K. But although, so our working temperature is 120 K for temperature, the detector at 80 K. Length. So right now here, I'll tell you, so we want 9 arc-minute by 9 arc-minute field. For given the plate scale of DOT, it's roughly 85 mm. So 85 mm, and the current mechanical system that we have for configurable slit, I'll show you in a minute, it has a width of 17.5 mm. So 5 we can fit in. But because we are using a special technology, we have to move, we are not using stepper motors, but piezo drivers. So the currently what we have set up has that width, but we can bring it down to up to 10 mm. When you go to larger telescopes, the focal plane is much larger, so you can easily accommodate 30 to 40. That's all. Yeah, right. We can go down. Right now we are, so see the way I'll show you in a minute. When you see the CSU, the way we have designed it, you will realize it. So these are the summary of the specifications. Wavelength, as I said, near infrared, and resolving power 2500, and slit width of. So we have optimized. All the designing is done for assuming a seeing of 0.8 arc seconds at Devasthal, and we sample it by 3 pixels, and so we arrive at that 9 arc-minute like that too. Yes, in real time you can decide. No, this is a 0.8 arc seconds seeing the stellar disk, so that is sampled. Yeah. So you can, so if you're observing a bright star, you don't need to have that. So you can make it very small. And if you're a faint star, you can, for the seeing, the spatial seeing. Yeah, spectral resolution, of course, it also depends on the. And field of view for direct imaging, 9.6 arc-minute diagonal. So roughly that. For spectroscopy, the field of view is 9.1 by 3.1. We can do spectroscopy. I'll show you in a minute, because you have to disperse the spectrum in the detector. So if the star is at the one end of the thing, it will go out of the thing. So anywhere in this 9.1 arc-minute this way, 3.1 arc-minute this way, you can put the slit on it and get the spectra. For the timing, 5 configurable slits. Even for DOT, we can increase it if we want. If we slightly change our thing, we are looking into that. So I told you 17.5 mm is the width. That is because the way we have set up the piezo drives and all that. But our engineers tell me that we can go up to 10 mm. So this can be more. See, the throughput is really so we have very few optical components. So it's a very preliminary estimate though. And grating, so YJHK and filters. Limiting magnitude, this is also somewhat preliminary. So take it with a pinch of salt, 16 magnitude in K. And of course, for imaging, you can go deeper. If you really see the figure, you'll understand. Because although you can image the entire 9.1, you can do for imaging, you have spectra, you have to also disperse the spectra, no? So suppose if towards the edge of your field, there is a star. So half of the spectrum will be outside the detector, right? I'll show you. Yeah. So this is the thing. So you can, so the moon is half a degree. This is our field of view, the red one. Imaging, you can do the entire thing. Spectra, you can, see now suppose you have a star here. You put a slit like this. Half of the spectra will be outside the detector. So until here, you can get the entire spectra. So in all the wavebands. So You can get, but some of it you lose. That's all. If you are only interested in this side of the wavelength, so it depends. Some wavelength you will lose, but within this 3.1 degree, you will get the entire. Yeah, of course you can choose. No, we have 5 slits. You can put it anywhere, in this one. Yeah. So that's a field of view. So that's what I'm saying. I'll show you an example when you see the spectra, you'll understand. Yeah, here it is. Yeah. Imaging field, 5 slits. So you can put it anywhere within this 3.1 and you'll get spectra like this. What you get on the detector is something like this. 5 spectra. Now, look at some of the key features of MOIS. What distinguishes it from some of the others spectrograph that are being discussed. So high throughput because we have very few optical elements. That is absolutely essential, and custom slit width that can be controlled in real time. That's an important thing, and extended object spectroscopy, more flexibility. You can put together all the slits into a long slit and get a galaxy spectra if you want. But you can also have probe different parts of the galaxy or supernova remnant or YSO jets. And reconfiguration time is only 2 to 3 minutes. I'll show you a video of how we move the moving slits. But the real strength, power of this instrument is not just a spectrograph, but also a wide field imager. A 9 arc minute image, YJHK imager, and also narrow band filters. And we have designed as a modular design. The CSU, you can just, so I'll show you in a minute when we discuss the optomechanical design. The CSU unit, the configurable slit unit, you can just slide in. So you can also scale it up for NLOT and TMT. And of course, we have a legacy for MOSFire, EMIR in infrared, and WFOS also had tried out this in the optical, of course. See, what we are proposing is MOIS as a facility instrument because it can do imaging and spectroscopy and do it both near simultaneously. See, you image a 9 arc minute field, and then whichever interested objects, you go and do spectroscopy. So almost near simultaneously. So that's the power of this instrument. So let's look at some of the science cases. So you can address a variety of science cases, ranging from transit spectroscopy of exoplanets. See, then when you do transit spectroscopy of exoplanets, see, the transiting exoplanets are very much more amenable to further characterization. You can do transmission spectroscopy. So to do accurate transmission spectroscopy, first, you need to have a reference star in the same field. And then you put the slit on that. So you simultaneously observe. Other thing is you should have the flexibility to change your slit width because this, depending on the brightness and all that. So generally you keep wide slits. And then, of course, extended object spectroscopy I talked about. And really low mass, substellar end of the IMF and freely floating planetary bodies. You can do both imaging and spectroscopy and time domain astronomy. So you can use the large field of view to quickly image it and then follow up with the spectroscopy immediately. Just put the bars in, right? I would say near simultaneously. You take the image and then yeah. Yeah, I said maybe a couple of minutes. I'll show you how fast they move. The point is, in none of the telescopes in India you can do this simultaneously. Spectrographs are different, So this is the flexibility and the efficiency offered by a combination of imaging and multi-object spectroscopic mode. Yeah. So here is another example of how on a galaxy you can place slits where you want. You can decide. Width you can decide. Yes, that's the whole point. Yeah, all need me. So they are all controlled by different. So you can have 5 slits, they can have different widths. Yeah. So I want to stress a couple of science cases. I mean, why this is what makes this instrument unique. So I talked to you already about wide field imaging and spectroscopy, large sample of stars or galaxies, extended sources such as supernova remnants and nebulae. So the MOIS can perform deep wide field imaging in the NIR broadband and narrowband, followed by multi-object spectroscopy. So you can do all this variety of science cases, a category of, a large class of science cases. But one of the things I particularly like is this ability to do near simultaneous photometric and spectroscopic monitoring of variable astrophysical sources. See, variability, if you can do photometric, if you can supplement photometric light curve with spectroscopic uh, time series, so that you can study a lot about the physical processes that are causing this variability. And this is extremely useful for time domain, transient studies and all that. And of course, extended object spectroscopy with varying slit widths and slit lengths. So you can put two slits together and make it a longer slit, and two slits here, or put everything together and make it the really long slit spectroscopy. For example, rotation curve of galaxies. You put one big slit and do that. And faint sources, because its throughput is high compared to similar spectrographs. So this can be a workhorse instrument really for a telescope. So you can have multiple faint sources, extended sources, point sources, what have you. So where are we so far? The progress made in the current status. So we have designed and developed a fully functional 3-slit prototype configurable slit unit in the lab. And we have demonstrated that it works at 140K. I'll show you in a minute. And we have a close to a final optical design. And we are currently designing and fabricating optomechanical subassemblies, the lens holders and the baffles and radiation shields, and designing the whole of our cryo jackets. And the third point, see, we wanted to develop our own controllers for, see, S2RG detector we had to buy. There is no other go. So in fact, we have just submitted after the seed money that TIFR gave us, we have done the proof of concept study. We have submitted a 10 crore proposal to TIFR. But detector takes half of it, it's 5 crores, the S2RG detector. But there is no other way,
Sliding all the slips simultaneously, right?
Not necessarily. You can separately. All each of them have different controls. No? 5. So you can do. That's up to you. Yeah, the whole thing. To get to a particular arrangement. So yeah. Yeah. So you can simultaneously move. You can first move one. So you have all that freedom. No, so that's a mechanical design. Right now, the mechanical. So because this piezo drives, they themselves are about 8 mm wide. So you have to support. Then we have verniers to accurately measure the location. All this backlash and all to avoid that. So that the 10 micron to get the 10 micron thing. So, but we are refining that. It's a little crude at the moment. So 17.5 is because of that. But we can come down up to 10 mm. That's what our engineers tell us. Yeah. That's exactly the point. I'm just trying to see. Is Pankaj or somebody here? No, he's not there. Yeah. Yeah, Arun, do you want to answer that question? How small can we go in width?
Yeah, so currently it's a physical limited by the physical size and how it couples the piezo drives coupled to the slit. But we are actually working on like a cascading kind of mechanism where you can put with the same drives more smaller slit. It's just like how do you arrange it mechanically? So it's right
Yeah,
now it's a very simple design which directly reflects the width of the piezo drives
right.
coupled directly. Yeah.
So there are the ways of doing the ways of improving that mechanical design. Yeah. So yeah, ideas welcome. So that's why I'm here. So to minimize the backlash and jerk, that is why we use the piezo walker drives, positioning accuracy, uh, and it can we get the required span of linear movement. And we use customized vernier scale and readout electronics for position accuracy, and prevention of light leakage by mechanical design of the slit bar, so one sliding over the other. Coupling of piezo walker, vernier slit bar, all this we have done. And here just show you some pictures of the assembly. So I think this is the 3-slit prototype that we have put together in the TIFR IR lab. So this is published. You can look at this paper. I can send it to you. All these tests. So we also then cooled them. We cooled them using this white things. These are copper braids. Just the slit. See this piezo drives. They work at room temperature. So we cannot cool them. This has to be outside our cryo. But the same company, they have piezo drives that works at cryogenic temperatures, but they're extremely expensive. 5 times more expensive. One possibility to buy them. If we think keeping out this piezo drives outside, if it makes our instrument too large, we might go for that. So we need some more discussion on that. Yeah. And yeah, this is a close-up of the 3 slit bars, So we have the knife edge here at the end of the bars, and they are the ones which form slits. And here is the prototype is control electronics. So all this will go into the CSU unit of the instrument. And these are the cooling curves. I just want to show you that. Yeah, this is the green line is to the one of the this knife edges. We have got it down to 140K. So we are hoping that we will be able to. So we ideally our operating temperature is 120K is what we are aiming at. So we have gone down to 140K. This need to further worked on for the three slit unit. Yeah. So So let me just show this video. You can see slits moving. So this is just a prototype, just to show you how we did this. Yeah. So they'll form slits at 3 different positions. So this is just a lab model. I mean, an original one will not have this, and we'll be a lot more sophisticated. But this is just to try out the driving mechanism and the electronics, all that. So. Yeah, that's about 120 micron slit. Yeah, completely close. So you can block the light also, and then completely withdraw and make it ready for imaging. Yeah. Yeah. So that's another advantage. So yeah. So there was a question. Was there someone? Saurav. Yeah.
Usually they like put like reflective surface.
Yeah. So this is just to so while cooling experiment, while we were cooling it, we did that to cool it further. But this is just a preliminary the prototype thing. Yeah. Yeah, you're right. Sorry, yeah, you have to reflect off. That's that's efficient way of any other. That we haven't studied yet, Kumar. Yeah, that's something. See, we haven't built the calibration into that. We have to see how. But in the optical design, I'll show you. We have tested the spectra at different locations in the thing and all that. So that they are okay. So this we haven't really looked at it, whether there's any wavelength shift and all that. But I can show you the Yeah. That we are yet to do that. Yeah, that we haven't done a study on that. Yeah. Yeah. It's very good. But within so that we haven't done. We haven't obtained a spectra yet with the thing. So that we haven't done. Yeah. But this is something I think. Yeah. This we need to try out and see if there is any wavelength calibration. How much of a difference does it make and all that? Yeah. Yeah. But that we need to test, and we need to have a hold on it, and we have how much it is. Optical design. So these are So first a window to the whole cryogenic jacket, and then the slit unit will go here at the focal plane. And then, so we want to have the slit unit separate because we want this vacuum to hold the remaining part, because if there is any issue, we want to take it out and do it, repair all that. We don't want to lose vacuum here. So we're adding another window here. Then a field lens. This is a fold mirror to make the instrument compact so that it will fit into the DOT main port. No. Finally, we need both because this slits will be here. No? Yeah. No. Slit will be cooled. Yeah. Slit has to be cooled. No, because otherwise it will. But the piezo drives will be outside. The electrons will be outside. Yeah. And these are the collimator lenses 3, and then camera lens elements 6. So 2 fold mirrors and camera. So and here is a grating mirror wheel for imaging. It will be a mirror, and we are using 2 grating. I'll show you. So this is also published in the SPY article 6 months ago. Huh? Yeah. It's on a wheel. So the exact design of the wheel we're still doing. We are currently thinking of a triangular shape. There are 3 things: 2 grating and 1 mirror. So, but their angle will be slightly different because grating will have to be a slightly different angle than the plain mirror. Yeah. So we are. I don't have the. Do I have the? So I don't have the dimensions here. Yeah, it will fit in the. So. Yeah, so that is why we wanted to make it a little compact. So yeah, and the pupil size is about 55 mm. The largest diameter, diameter of the largest optical component, the power element, is about 1.5 mm. That's this field lens. See, when we were trying to do this, when you do this wide field spectrograph, if you go beyond 100 mm in optical components, the price just shoots up. So we this was something necessary. I mean, otherwise we just couldn't make it. So anything above 100 mm will have to be custom made, and it's and especially if it's power element, it's prohibitive. So we are keeping it around 100 so that it's so we got a couple of codes, so they are manageable. With our funds, we can do it. No, there's no cross dispersion. What filters?
Order.
Yeah. But also, we will also have narrowband filters as well. Yeah, yeah. No. So didn't I? So we are using different orders for different filters. So the detector. So for a given rating, for Y, J, H, K, they are observed in different filters. So it will fall there. So it will not fall in that same location where the detector is placed. Yeah. Moving on. So this is the grating. See, again, to slightly save on the cost, there was two off-the-shelf gratings we could see in Richardson grating catalog. So we thought we could use it. It roughly matches our specification. See, if you buy a off-the-shelf grating, the cost is drastically reduced. So we are hoping to do that, but the sizes are slightly different. We have in correspondence with them, asking them to give it to us, say something 100 by 100 or so. So, yeah, if you have any question, I don't, do you want to comment on this, on the grading thing?
Nothing much, like, so we are using off-the-shelf grating, and
Yeah,
we are using two gratings because even though like the orders of we are also using order sorting filters. That's why we don't need cross dispersion, so the orders don't fall on each other. So having the filters, and the other thing is that we use two gratings because we want to match the peak of the blaze efficiency to center around where the filter center wavelengths are. So that's about it. Yeah.
yeah. So that's what you were saying. The peak efficiency roughly falls there. If you use only one grating, it doesn't exactly. So if it is okay for H and K, then it's not so okay for Y and J. So that's why we are using two gratings. Moving on. Yeah, then we did various uh, trade studies of the optical model. So here is one for the slit profile, the center of the field. This is the fraction of peak energy, and so within so this will be about 27. Yeah, half the point source radius. So it's all well peaked. This slit enclosed energy is a better indicator. Even at the edge of the spectroscopic field, about 80% of the encircled energy is within 20 micron radius. This is just to show you the spectral layout. This is better. So just to show you how the spectra will look like. If you place slits like this, then this is how you get spectra. This is in K band, and similarly in other bands. No, there is no overlap. No, the slit length is fixed like that. So it's just yeah. So there will not be any overlapping. Yes. So that the way we have so one, it slides over the other, so it doesn't spill over. That we have taken care. And we have done a detailed tolerance analysis. So both for alignment tolerances and fabrication tolerances. So even if we buy optical elements, they might make it for our specifications, but still they may be off by plus or minus, whatever, 100 microns or so. So these are the thickness, radius of curvature, surface regularity, and surface descent. All could be off. And then once we have those, the way we align them, that also can reduce, so what Arun has done is run a huge Monte Carlo model, first separately, alignment alone, then using the fabrication uncertainty and all that. So in I think here, yeah. So this is the number of times. So it's almost 80% of the time it falls within 3 pixels. Given this tolerance is sort of okay, and yeah, this is for the center of the field, and the next one is for the edge of the spectroscopic field. That's about, yeah, slightly less than 80% or 75 or something. So still okay. And this is the spot size. The color scale indicates spot size. So the blue is 9.2 microns and the red is 34.5 microns. So except towards the edge of the field, it's okay. The blue things should be okay. So when you go, see in the wide field spectroscopy imaging, there's always a problem. When you go towards the edges of your field, it slightly degrades. But this is, so we want it to be within 20 microns. So towards the edges, it goes to 30, 34, sort of okay. again, the different kinds of tolerance things that Arun has done. Yeah, this is the temperature tolerance of the optics. We designed our spectrograph for 120K. And for 120K, this is the thing. And even if we are operated 140K, this is the kind of degradation. So this is what is shown is the radius of the 80% encircled energy. So 120K, we have optimized it. But if it is 140K, it goes from about 18 microns radius to 20. Yeah, so slightly degrades. So we have also started now. Now we are in the process of optomechanical design and fabrication. So we are so this is how it will look like finally. This is a very preliminary thing. That's the CSU unit where you will have the configurable slit and then the spectroscope behind. So each of them will be separately evacuated. I mean, so the one we can remove the CSU if you want, and various other components, the filter wheel, the grating. So this triangular thing is the grating wheel. Yeah, this is still in the works. And Arun has also done preliminary stray light analysis with these components, with this filter wheel and other things. So what to look for is the red dots here are our observed spectra. I mean, the spectra points. So that's about 10 to the 3 or so. And the green is the stray light. So that's several orders of magnitude low. So 0th order, it looks okay. We need to further work on this. And H2RG detector, as I told you, so we have already started testing leach controller with H2RG ROIC. We have bought this ROIC to test the electronics. So Sailesh, Bhagat, and Savio are looking into this. And Savio, of course, is the overall in charge of the whole spectrograph project. Yeah, so the final 2 things that I want to mention is Arun has already developed a MOIS simulator and exposure time calculator. So what you see here is if you put spectra here, the slits are here, and then you put the stars here, and this is what you get. So he has used the sky data from Devasthal, but the telluric lines from Monarchia, I think. So this is how the horizontal line is your stellar spectra. He has simulated this for Vega spectrum. And the vertical lines are the telluric lines, OH lines mainly. And if you take a cut, this is what you will see. These lines are telluric lines. And yeah, this is just a blow up of the whole thing. And if you look at the signal noise, you can see where OH lines are, the signal noise are very poor. So telluric removal is an important thing. So this is just being developed so things work. So exposure time calculation you can do this way. So there is a tool. So I don't know if yeah, so this is already on GitHub. You can try it out if you want. So we have made it available. And yeah, one of my students, Himanshu Tyagi, is developing this observation planning and slit configuration tool. So what you do is he has this GUI. You give your target name, which is sympath recognizable. So it will upload the 2-mass image. You can decide which image you want to load, 2-mass or WISE or whatever. It will load, and then you can place the slit wherever you want, and then your instrument will do the same. So slit 0, slits 1, yeah. So these are the 5 slits. This GUI in the user end works, and we have been able to communicate to the CSU, the configurable slit unit. So it's still going on, but so we have made good progress there. So final takeaways is that the optical design is close to final. We are currently doing the optomechanical design and cryostat design going on. We already have a raw data simulator, preliminary strain analysis done. And we are now thinking of procuring the optical components, at least not the power elements, at least the other ones, windows and fold mirrors and other mirrors and filters, YJHK filter and narrowband filters. So we have some money left in that initial 2 crores. So, but although I say optical design, so there's a scope for improvement, modification. So I'm here to welcome you all to be part of this project. So Arun is in IAA, so we are also getting help, trying to get help from IAA. See, all this is with a long-term view of NLOT. So any instrument we build for NLOT, it has to be a multi-institutional consortium. I don't think a single institute can build it alone. And we also want to build our instrument building capacity across the institutes too. So I'm here to sort of invite you to be part of this, and plenty of scope for adding, modifying science cases and also instrumental design. So if you have a specific science case which you think this particular design is not really optimized for, we can talk about it. We want it as a facility instrument, not specifically for one. See, MOONS is optimized for this fast survey, so it has a different philosophy. So we are thinking of it as a facility instrument, so that to accommodate as many science cases as possible. So we can talk about, if there is some design changes required. We can discuss all this. We are quite open about this, and yeah. So more important is we also parallelly would start designing for NLOT also, scaling this up. From whatever we have learned so far from our experience. So at the ASI meeting, there is a workshop on 31st. So Arun has already started looking into that. We might have a poster on how will it look for NLOT. I mean, it may not be a simple scaling. There will be a lot of issues, but we have to start somewhere. So yeah, suggestions, comments, welcome. Yeah, so please, be part of this. Yeah, there's a question. Yes. Yeah, there was a question there.
I mean, I just wanted to ask what were the possible constraints that you faced when implementing the 3-slit design, like the physical constraints that you faced? That you have to
Physical
overcome.
driving, it was the main problem. So yeah, with the once we had the piezo thing going. So yeah, so what we did was we bought these piezo drives. They're very expensive. They're we paid in euros. So we bought two. Then our engineers, sort of reverse engineered, and they developed their own. So we only bought two drives, but the piezo thing we need, but the drivers we bought only two, and then now we can. Pankaj Madhwani can do it now. So they kept asking us why you bought so many piezo, but no, don't you need the drivers? So we said, okay, we are managed. So yeah, that was the most challenging part, and then rest of us, just you learn from the experience and do it. But piezo gave us this flexibility of the placement accuracy. That was much better than anything that we could get by stepper motors.
I mean, what was the advantage of that piezo walker design?
So placement accuracy. So you need so you can exactly play within 10 micron accuracy. You can place the slit. Our slit width is 120 micron, and in the field of view, if you have an object and if you want to place it, you can place both the bars, both edges of the slit to within 10 micron accuracy. So that is, and the movement is also quite fast. It's much more easily controllable and all that. So.
I have a question. So the TM mode, there's 8 slits, right? Stepper mode.
See, it's not. Yeah, T-moons have a very different design. No, it just pickup arms, robotic arms, which picks up things and then put it on a slit. So it's not.
They have degrees of freedom, like to be placed in any angle.
Yeah. So So there is a So you can place it in different angles too, but then it's all done by the robotic arm. So that's a little more complex mechanism. The front optics is much more complex there. CSU. Yeah, so 85 mm like this, and then even if we withdraw this, it has to go completely out. So and then you have to put it on. So the entire cryogenic jacket we are still designing. So it is about 98 to completely got about 110 mm or something. So 85. So if you put it all, that's one side. So yeah. So the whole, the dimension exactly, I don't remember. I need to see. Arun, do you know? Do you remember the entire size of the CSU?
The CSU only.
Yeah, CSU.
So the CSU comes around like I think 300 mm ish, like the whole thing with the 80.
Yeah, if you including the housing and all that.
Yeah. So anyway, like the cryostat itself, the front end also will be around 500 mm, like half a meter.
The whole thing, the compact design I showed. The longer dimension is 500 and the shorter dimension is about 300 or something. Yeah.
I was just wondering whether we can utilize this CCU for the cost design also, because In POSC also we are using the slit size of around 80 mm. In the current scenario, it is not possible because we
Okay.
do some
Yeah, that's it.
mechanical.
It will be easier because you don't have to cool, you don't have to cool it to 120, 140K.
But for POSC, we didn't need the cooling part.
You don't need. Yeah, exactly. So that's interesting. I can talk to Pankaj and Kuti and see if they are interested. So I'm talking to Brajesh and Kumar also. I'll talk to Dibangar as well. I'll come back here in late February or March with our engineers too. So they want to have a look at the Devasthal telescope and have a feel for what. So this is an interesting suggestion we could
That way we can have
explore.
multi-object spectroscopy in optical range also.
Yeah. Why not? Let's explore. Arun, do you want to comment on that?
On what?
So the suggestion is DOT has an ADFOSC instrument which currently is a single slit spectrograph. You can probably use CSU there.
Yeah, I did.
See, our design is modular, no? So if we can just put it in there, we can explore. I don't know. I haven't thought about it. Yeah.
Yeah, we'll have to look into the design, like
Because
because the CSU itself is like large enough component to that's probably the only constraint.
It will be less challenging than near infrared because the cooling is not required. So we can certainly explore that. Yeah. We have optimized optical design for 120K, but we have achieved 140K so far. In lab, we have demonstrated 3-slit. We want to go down. We'll see how yeah.
How you are planning the cooling? LN2 or closed circular both?
Oh, in the final thing.
Yeah.
Yeah. So we are seeing if we can. We should not. We don't want to use closed cycle cooling. Just with LN2, we can. But we are just designing the optomechanical part. So. See, the closed cycle cooling, it'll add vibration, everything makes it complicated. In TANSPEC, we have that. We don't know. We are not sure if we can. So this we have to discuss with. I don't even know if TIFR alone can do it. We might ask for some external help or something in the final thing. But right now, the plan is to just use LN2.
Yeah. But why did you set it 120K? Because TANSPEC is using it 75K.
No, detector will be at 80K. This is the entire spectrum. TANSPEC, the rest of the thing is at 120K. Okay. Yeah. So the below 120K. Yeah. So TANSPEC. So here also the detector will be at 80K. It will be LN2 will be closer to the detector. The other thing will be So because see, there will always be some gradient. So 120K. We don't want anything other than 120K. So at least the spectrograph we had designed right now our design is for 120K. Arun, you want to comment on that? Krishna's question is, why did you, the 120K thing?
No, it's usually like the optics which is away from it, right? The detector part where you have the cold plate for the detector. It's usually like at a gradient, and it's so the kind of MOSFET also they optimize the optics at 120K. So a lot of these instruments have the optics a little bit higher. So it's mostly getting the refractive index correct for these optics at that temperature. Yeah.
Okay. Just one last question. You have not shown the arrangement for guiding and calibration.
Yeah. So that we are still working on it. Yeah. So that we have to have. Yeah.
Possibility to keep one of the 5 slits a little longer and just try to track in the spectra interaction. And just try to see if it's possible to develop a tracking system for that.
Yeah.
So
by guiding, you mean, yes, it's a multi-object spectrograph. You can do it. So you mean some optical star in somewhere or something?
Yeah, some bright star in the field because there's a.
But if you have multiple options, you can see it in the detector. You can. Yeah. So we had to. Yeah.
There is also an interesting way because some of the H2RGs allow for fast readout mode of certain windows in the detector. You can actually open up the slit and also use that for guiding, on instrument guiding. But it's all like a little bit
complicated. Is adjustable. No, it needn't be 0.8. It can be 0.5 also. If the bright star, your slit can be very small. So you lose light, but you don't care because the star is bright. And if it is faint star. But yeah, so to answer, we haven't, yeah, we need to, the guiding thing we have to, yeah, Kumar, I agree, yeah, we have to think about it. So one of the things Arun was saying was this sub-array readout mechanism. So you can do the fast readout and correct for it. But then you need to have a mechanism for fine adjustments, so that we have to see.
In any case, we have got to use the spectrograph optics. So the one way would be like one of the 5 slits can have a larger width, so that you can track in a spatial direction the motion of the stars. And using that, you can have a feedback if there is a provision for a fast readout by S2RJ. I mean, this is just
no, so yeah,
can be thought
Yeah,
of because
yeah.
once you're taking a
Yeah.
spectra mode,
yeah,
then your entire spectra optics is coming into play. Now I had another thing, like while comparing the tan spec sensitivities, how will it compare?
See, we have a sensitivity calculation, but it's very preliminary.
Just rough.
Yeah, so I showed, so 16 magnitude in K is what we can go at the moment because our throughput is good. See, tan spec also has a cross dispersion and all that. So ours is the optical design is much simpler. I mean, it's very minimal. So our throughput is good. So
should we take that it's at par with tan spec?
I think it's definitely at par with. See, we had to actually demonstrate before we talk. No, so our simulator shows we can go up to K16 magnitude, but that depends on some of the assumptions that we have made.
Okay.
But definitely as faint as tan spec, definitely. But perhaps because our design is simple and fewer optical elements, perhaps slightly better.
Yeah, we are also increasing in terms of imaging area, so it could be said
Yeah,
it's a true successor for tan spec.
Yeah,
Say that.
yeah.
And I had one more query. You mentioned MOSFET and kick.
Yeah.
So any idea? I mean, this while guiding a star, I mean, what is the scheme they use?
I need to check
how long is
that,
the requirement for this system?
Yeah, I need to check that. I don't have it right at the top of my head. So I'll get back to you on that. Yeah, that will be interesting. See, with MOSFET, we were in touch. We were trying the CSU thing. They had successfully built it, right? Then they told us that they actually outsourced it to a Swiss company. We call it a Swiss company. Then they said they outsourced it to someone else, and that that company is not there anymore. So one of the things that they faced is that, a lot of outgassing when you started cooling on this material. So we had to go through all that. But there was, so we were, while cooling the street, we experienced some of it. But we finally got down to 10 to the minus 5 millibars. So we could get down to that kind of thing. So, but with this we'll have to, we'll have, this guiding thing is a good question. Another thing is the calibration unit thing that we haven't tried. And I know some of the tests we should do, whether the wavelength calibration changes with this 5 slits as a function of the location in the field. That's questions. Yeah.
So outgassing, you mean for the slit?
Material, yeah.
So this was currently this tested in vacuum.
Yeah. So we also experienced. So it took us a while to get to that. So you have to really pump it out, and when you first cooled it,
Yeah, but in spite of getter and all, it
finally we achieved that kind of pressure.
What is the material of this slit?
It's a steel, one particular kind of steel. I need to the knife edge is at the edge, and then the bars.
Yeah.
So it's a steel. What is that generally? So
SS.
Yeah, one of those. Yeah.
Some stainless.
Yeah. Right.
So sometimes this, most of the cases, this piezoelectric actuators, they exhibit some hysteresis. So I don't know whether case.
So we have calibrated out.
Okay,
so Pankaj could do it. That is why we have this vernier. We exactly can calibrate the.
Okay, so that again for the temperature you again have to calibrate.
Yes, we have done it. So while cooling down, we tested all that. Yeah, we can do it. But one issue is because this is something that this doesn't work below 0 degrees Celsius. This piezo drives. So should we buy cryogenic? So there are piezo drives that works at cryogenic temperatures. So one possibility is to buy them and use them. So that'll make the instrument probably a little more compact. So that is something that we are contemplating. But our fund then, it all go up,
No,
right?
because this provides 10 micron accuracy, if it's well calibrated. Otherwise, you may have to have some feedback mechanism
Yeah.
to see, in addition, that whether it has reached that position or not.
Right. So that we have checked. That we have checked
Okay.
in both at room temperature and at 120 while we were not 120 while we were cooling. So that we can read off that with the vernier. Yeah. The exact thing. So I wish if Pankaj was there online. So yeah. So Arun, do you know how this 10 micron accuracy, how the read off thing? Pankaj is not online.
So they have a digital vernier that is kind of like giving the encoder kind of thing. But also in the final instrument, we will always be able to calibrate using the detector itself, because these slits will be imaged by the detector, right? So a lot of the finer movements, like you can have a calibration frames taken for its movement and calibrate it using the detector itself, like the optics, spectrograph optics. The major mode, yeah.
Yeah, in the lab model, what they're with using the vernier, our least count of 10 micron is the vernier, and we can't go below that. So piezo drive is capable of giving you better. But I'll check. I'll write back to you. Let me check with Pankaj exactly how Yeah. But this is our limiting thing, is this vernier, digital vernier thing. Yeah. Yeah. So that's the thing. Exactly. Yeah. So so that is that's my understanding. So it's 10 micron is because of the digital vernier. We can measure only up to that. Yeah. So I showed you the configuration tool, right? So the observer, this will be what we finally want to do is something like this. So this GUI we have, you put in your source coordinate or some symbol, and then you load the field. Let's say 2 mass, and then you can move the slit and place it exactly where you want. Now we want this to communicate to the CSU electronics so that it can move. So we have been able to successfully do that. But now the sky coordinates have to be there has to be a coordinate transformation done. The sky coordinate have to be transformed into the CSU detector pixel coordinate or whatever, or how the CSU. So if we are tying the CSU down to pixel detector thing, then we have to do that transformation. So we are currently doing that. Yeah. So no, this is the GUI. Will be a software, So you load it, and so then now you will have the sky coordinates, right? So you establish a coordinate system. Now you have to transform this to the coordinate that the CSU and the detector understands. Mm. Mm. Yeah. So that, yeah. For short exposures, not, but
Lighting would be required.
Yeah.
I think this is a good suggestion that from detector itself, in
Yeah.
lighting,
So
just try
you mean you have to
to
constantly have a loop? I mean, you keep. Speaking mic, no? Yeah.
after identification, you can take the input from the CCD and transfer it to the slits. In that case, guiding is not necessary. And long also, depending on the tracking distance,
But you just run the constant loop. Yeah.
You can adjust the slits also.
Yeah.
No, no.
Know whether it has moved out of your place. You need some,
Before movement itself, if it identify where which direction it is moving, in that way it can adjust, right? Slits. In that way it can move, right?
Yeah.
Yeah, that's what.
instead of guiding, going for the guiding, if you implement this kind of mechanism, because we know the pixels from the imager and say imaging mode.
Yeah. So we have to look into all that. So yeah. So suggestion, ideas welcome. So most welcome. Arun, do you have any comment on that?
Oh, I couldn't follow here most of it, but yeah.
Yeah, I think we can take the discussion offline. Yeah, we can talk. But yeah, all good suggestions. We haven't the guiding part we need to still work
Yeah,
out.
I think I mean, this discussion, actually, there has to be a crosstalk between the user interface, GUI, which you are getting the state position in RA deck. With the detector position, immediately it has to reduce the data and get the positions there. So one crosstalk is required there. Once the detector position is known, you again send that information to the slits, CSU, and let CSU work on that.
Yeah, that's something.
Guiding is another aspect, I think we
Yeah,
need.
that is a great suggestion actually. Like,
Yeah. So this is
to
what
also
Krishna,
control the slit position
Yeah.
according to guiding. Yeah.
No, you have got to see typically in infrared. Yeah. Typically in infrared exposures are short. We do multiple exposures, so it's not a serious one. But we still need guiding to ensure that Yeah. See all this will So we have to also see our instrument is already big, so we have to make sure how to make it compact. But yeah, but this suggestion is interesting. Yeah, we need to look into this. Yeah. Any other suggestions? Huh? So 0.8 arcsecond seeing, we are sampling it by 3 pixels. Yeah. So something like that. Yeah. But that is by design. So we want a 9 arc minute field, and we'll do that, and and then the whole thing. So we want a 9 arc minute. Given the plate scale of DOT, it translates to 85 mm. Then we are going to reimage it on a 2K by 2K, which is 36 mm, right? 18 micron pixel size, so 2K, 36 mm. So that is 2.3 demagnifying factor. And that automatically works out to be 3 pixel. We also, if as a later stage, maybe put it behind an adaptive optics things, to further. I mean, we are talking about it. It will definitely improve the sensitivity. Yeah. Yeah, but nefarious is a multi-purpose adaptive optics. So multiple instruments can work behind. So you have to, your instrument requirement is that it has to work. I see. Yeah.
It's a 4-channel route or 32-channel? What you are planning?
Readout. We have not bought the thing yet. So what? So with we are developing the controller with Leech and the ARC controllers. So Sailesh has tried out all 3. He has worked out that we have ROIC that we can read out. So he has tested all those. So he has programs ready. We can do any of those. But then we have to decide how exactly we want to do it. Yeah. So this detector is going to drive our cost. It's 5 crores. So that's, and then the optical components. So that's thing. Let's see how it goes now. What TIFR does. If they. Yeah. No, this is we are talking about 5 years down the line, 5-6 years, because second generation instrument, right? So by then the current first generation instrument, see, you may not want to continue with some of them. You might want to decommission some of them. Yeah. I'm talking about 2029, 2030. So yeah. Yeah. See, the problem is, so then, if we go to long wavelength range, telescope, since the reflectivity, all those issues. But yeah, so we'll have to see. Yeah. Yeah, we have to think of this such, yeah, once we go towards NLOT, the instruments will get more and more complex. Yeah, yeah. Yeah. So the difference here is we can image. We have a wide field imaging. In T-moons, there is no imaging facility. Yeah. See, we had see. Let's make something simple first. See, yeah. See, we have to first do something and demonstrate, right, before we can take up. Yeah. 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 No, first let us make one, and then you know. Yeah. Yeah. No, but eventually we want to go there because you want to minimize it. But right now, see, we haven't really built complex instruments, right? So we have to first try this and then go step by step.
There was a deep plan or this fiber.
Why? See, fiber is not as efficient. So this is slits are much more efficient. The throughput, fibers always have this problem, right? So even in WFOS, I think they discarded the fiber in favor of slicers, I think. The fibers and IR fibers.
Also is fiber.
Yeah. Yeah.
Same fiber cannot be used for both of them.
Yeah. And then there are transmission issues and all that, Yeah. Yeah. So we'll have to, but NLOT, it's yeah. We'll have to look at that. No, not necessarily. We can always have the front optics different, but NLOT design is not frozen entirely, although there is some. See, it has to be a multi-purpose telescope. I mean, it can't be specifically designed for something, So we have to see, yeah. But this yeah, I had to look into that. Yeah, so we want to. But this is specifically designed for F9 and this prototype. We have designed it for the DOT. Yeah, but yeah. Yeah, but how many robotic? You can't have 44 robotic arms, right? So that makes it complex then. So this is why this is a kind of modular thing. So it's easy to increase the numbers. Thank you. Thank you for your time.